Hello everyone, welcome again to this video, and in this video we are going to talk about expectation of continuous random distributions. So we already know what expectation is from our previous encounters with the discrete probability distributions, and it's just the average value, and the formula we defined before was for discrete distributions, which was in terms of summation. So we are going to do the exact same thing here, but we are going to do that in terms of the probability distributions which are continuous, right? So if you remember, it was like x into f of x dx for continuous distributions, and x multiplied by probability of x equals to x, and summation over all x for discrete distributions. So we are going to get to that part. So let me give the heading, which is expectations and higher moments so this would be the topic for our coming video, and it might span over 2 or 3 videos because obviously these are a bit tired topics and we would try to look into it very deeply. We might have to cover a lot of theory for this, but we shall do that in time. That is not something we need to worry about. So let us start with the definition. So this is basically the definition for expectation of a continuous distribution which for a random variable x. So expectation of x is defined as integration over the real line x into f of x dx, where f of x is the PDF of the random variable x, right? So this is also called the first moment. So e of x is also called the first moment. Now the variance is something that will also be defined in terms of higher moments, but first let us understand how higher moments work, and then obviously we are going to take examples one by one to find out what comes first and what comes next. Okay. So the nth moment of an RV or a random variable x following a PDF x is given by x to the power n into f of x dx. Okay. So this is basically the nth moment, and also this nth moment here, what we are studying here, is basically something that will help us in finding some properties of probability distributions like skewness, like variance, the MGF and stuffs like that. And we'd also understand how to find these moments using the MGF as well, so it's like a reverse process, but the MGF is if not harder, it's at least as difficult as the moments to find. So probably finding the MGF is a better way of finding higher moments, and we can basically sum them up all in an infinite series. We shall see in time how to do the MGF part, as we have seen for the discrete distributions as well. So let us take some examples. And from this video onwards and the next videos, what we are going to do is we are going to take a few examples and understand how to find the higher moments. So distribution number 1 which we are going to see is exponential distribution. Now if x follows exponential of lambda, then this PDF is already predefined for an exponential distribution, so it's a matter of memorizing it. And we already saw in the last video how this is actually a PDF, because we did check that the total probability was 1, and we also checked that the function is non-negative. Now let us find the first moment. Which is also called the expectation or the average value of the function, that is e of x. Then by definition e of x is now it's just a matter of time to evaluate this integral, right? Okay, so let us begin the process. So what I will do is I will just write down the solution first, and then I'll come back and explain to you step by step what I did and where I did. So up to this part, let me explain. Obviously the expectation of x is given by integral over all real line x into the PDF of x, which is fxx dx, and the real line means basically minus infinity to plus infinity, so we just rather put in the limits, which is minus infinity to plus infinity x into fxx dx. Now as we know, we can divide the integration region into two parts, because the exponential distribution is only defined in the right half of the whole origin, which is for x greater than 0. So this part where minus infinity to 0 x into fxx dx is there, this would be 0 because the PDF is identically 0. Well, this part, the 0 to infinity x fxx dx, will amount to the actual expectation for the random variable. Now putting in the value of f of x, we get that the resulting integral is lambda times 0 to infinity x into e to the power minus lambda x dx. Now we shall learn a general formula for evaluating integrals of this kind, where we have a power of x and e to the power some constant minus x. but for now let us use IBP. And you know from the eyelet rule that when you have an algebraic function and an exponential function, the algebraic function becomes the first function, right? So we apply IBP here. So this is the answer. Now for the explanation part, let me go back because there are a lot of things that needs to be explained here. So we did explain up to this part. Now when we are applying IBP and the first function is x while the second function is e to the power minus lambda x, so we see that by applying IBP we have lambda outside, and then we give a whole third bracket. Now this was the first function and this was the second function. So as usual, while doing it directly on a definite integral, integration by part works as follows. We write this first function x multiplied by the integration of the second function, that is e to the power minus lambda x dx, and the result, whatever the result comes out as, we evaluate that directly from 0 to infinity. Similarly, here we have 0 to infinity. The differentiation of x is 1 with respect to x, so because like ddx of x is 1, and again we have the integration from 0 to infinity, this time with the limits. Now this limit x by lambda into e to the power minus lambda x from infinity to 0, this becomes 0 because the first term, obviously when you put 0 it becomes 0 into 0, 0 into 1 which is 0, and when you put infinity it becomes a limit which is x by e to the power lambda x, where x goes to infinity, and it can be shown that this is 0 as follows, because limit x tends to infinity x by e to the power lambda x, it can be shown that limit x tends to infinity x by, and now if you use the Taylor series you get lambda x plus lambda square x square by 2 factorial and so on, right? So once you divide up and down by x, what you get is this 1 by x plus lambda square x and so on. So it basically means 1 by infinity, which is 0, because x is way smaller than e to the power lambda x, and that is why the denominator widely outclasses the numerator, and it's much larger, much larger, and grows even larger. So that is why the answer is basically 0. So that being said, this limit here is 0, and for this integration we still know that 0 to infinity e to the power minus lambda x is 1 by lambda. which gives you a lambda outside, and a 1 by lambda squared inside, which gives you 1 by lambda as the expected value. So this completes the portion where we had found out about the expectation of the random variable. So in next sections or in the next videos, we shall also find out about higher moments of exponential distribution, and would discuss about other distributions too, their MGFs and their properties as well. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems in theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.